Normal form representation. Normal form representation is how we want to describe static games of complete information. A static game is a game where players choose their actions simultaneously. Complete information means that payoffs are common knowledge, which means that each player knows the other player's payoffs. So a static game of complete information is a game where players choose their actions simultaneously and payoffs are common knowledge. We're going to start with an example. This is a famous example in game theory called the prisoner's dilemma. We're going to start by describing the prisoner's dilemma in words, and then we're going to show a normal form representation for this game. Two suspects are arrested, but the police lack sufficient evidence to convict them. The police hold the suspects in separate cells Now, this is an important point in the prisoner's dilemma that each prisoner is held in a separate cell. So each prisoner doesn't know what the other prisoner is telling the police. And describe the consequences of possible actions. So these are the consequences. If neither confesses, both are sentenced to 1 month in jail. If both confess, then both are sentenced to 6 months in jail. So if neither confesses, they both get 1 month in jail. If both confess, they both get 6 months in jail. Now, if one confesses, but the other doesn't, then the confessor will be released immediately, which means they get 0 months in jail. But the other will be sentenced to 9 months in jail. So the final option is if one confesses and the other does not. In this case, the confessor gets 0 months and the one that doesn't confess gets 9 months. Now we're going to show this game in what's called a bimatrix. And the bimatrix of the game looks like this. On the left side, we put prisoner 1. Prisoner 1 has two options. Either they can stay quiet or they can confess. On the top, we're going to put prisoner 2. Prisoner 2 has the same options. Either they can stay quiet or they can confess. Now, if both prisoners stay quiet, then they both get 1 month in jail. So their payoffs are both -1, because obviously going to jail is a bad thing, so the payoffs are going to be negative. If both confess, they both get 6 months in jail, so the payoffs are -6 and -6. If one stays quiet and the other confesses, the confessor gets 0 months and the other gets 9 months. So the payoffs are 0 and -9, and if it's the other way, then it's going to be -9 and 0. Now, this is called a bimatrix because it's a matrix, but in each cell we have two values. The first value in each cell is the payoff to player 1, and the second value is the payoff to player 2. So, for example, if prisoner 1 chooses confess and prisoner 2 chooses quiet, that first value there is the payoff to prisoner 1. Prisoner 1 gets 0 months in jail. The second payoff, -9, is the payoff to prisoner 2. Now, this bimatrix is an example of a normal form representation. And this is because it provides three pieces of information. The first piece of information is the players in the game. The second piece of information are the strategies available to each player. And the third piece of information are the payoffs received by each player. So a normal form representation provides three things: the players, the strategies, and the payoffs. Now, if we take a look at this bimatrix, we see that all of the three things are given. The players are given, those are prisoners 1 and 2. The strategies for each player are given, quiet and confess, and the payoffs are also given, those are the values in each cell. The next thing we're going to do is we're going to talk about the general case of a game and the notation involved in describing a general game. So we're going to be talking about n-player games. In our example of the prisoner's dilemma, obviously there's two players, so n equals 2. The players are going to be numbered from 1 to n. So in our example, we have players 1 and 2. An arbitrary player is called player I. So in our example of the prisoner's dilemma, I can be equal to 1 or I can be equal to 2. Capital SI denotes the set of strategies available to player I. We refer to this as player I's strategy space. So in our example, the strategy space for player 1, S1, is equal to quiet and confess. And the strategy space for player 2 is the same. It's also quiet and confess. Of course, not all games will have players all having the same strategy space. That just happens to be the case for the prisoner's dilemma. Lowercase si denotes an arbitrary member of the strategy space. So in other words, it's an individual strategy because the strategy space is made up of all of the strategies. So for example, if I wrote lowercase s1 is equal to quiet, that would indicate that player 1 chose the strategy quiet. If I wrote lowercase s1 is equal to confess, that would indicate that player 1 chose confess, and so on. If I wrote a lowercase s2 is equal to quiet, that would indicate that player 2 chose quiet. S1 to Sn denotes a combination of strategies one for each player. So again, in our example of the prisoner's dilemma, if I wrote confess quiet, this would indicate that S1 is equal to confess, which means player 1 chose confess, and S2 is equal to quiet, which indicates that player 2 chose quiet. So this is a combination of strategies. UI denotes player I's payoff function. Now we use the term function here because the payoff depends on the combination of strategies chosen by the players. In our example of the prisoner's dilemma, we have a payoff function for player 1, which we write U1, and we have a payoff function for player 2, which we write U2. UI of S1 to Sn is the payoff to player I if the players choose strategies S1 to Sn. So, for example, if I wrote U1 of confess quiet, this would indicate the payoff to player 1 when player 1 chooses confess and player 2 chooses quiet. So if we take a look at our buy matrix, the payoff to player 1 if player 1 chooses confess and player 2 chooses quiet is right here. It's going to be equal to 0. U2 of confess quiet would be the payoff to player 2 if player 1 chooses confess and player 2 chooses quiet, which if we look at our buy matrix, it's going to be the number right next to it. It's going to be -9. That's the payoff to player 2 if player 1 chooses confess and player 2 chooses quiet. Now we can define normal form representation in the general case. The normal form representation of an n-player game specifies the player's strategy spaces, capital S1 to capital Sn, and their payoff functions U1 to Un. We denote this game by capital G, which is equal to S1 to Sn, the strategy spaces, and U1 to Un, the payoff functions. Now there's one important thing to keep in mind. A game can be a static game even if the players don't act simultaneously. And the prisoner's dilemma is a good example of this. So in the prisoner's dilemma, the prisoners are held in separate jail cells. So it doesn't really matter if they make their decision at the same exact moment. As long as they don't know what the other person is choosing, it's as if they're acting at the same time. So this still means that it's a static game. So players don't necessarily have to move at the same time for it to be a static game. As long as each player doesn't know what the other player is choosing, it's considered a static game.